Okay, now we look at the problem 21.2. The question is to find the local extremes for the following three problems. So when we see the finding local extremes, that means they could be either local maximum or local maximizer or local minimizer. Okay, if it is local minimizer, then just apply the method we studied in class. If you're looking for local maximizers, then just take the negative of the objective function and then do the same thing to minimize the negative of the objective function. So, so to show this just as an example, I'm going to show the number 2 here. The number 1, number 3 are similar, but the computation are much more complicated. I think probably the number was not, they were not chosen so well to for hand computation. But the procedure for solving them is the same as solving this one here. And also to just show you the idea, I will just show the local minimum and the local maximum. As I said, just take the negative of the objective function. Okay, so now let's look at this problem. We are trying to minimize, trying to minimize the objective function, which is x1 square plus x2 square. And there are three constraints, three inequality constraints, these three, and I define the constraint functions g1 as negative x1, g2 negative x2, g3 is negative of this. Remember that we want to define them in a way that it turns out to be less than or equal to 0. Okay, because if this is the case, then we'll simply have the Lagrange function. If we only have inequality constraints, then we only have the KKT multiplier mu here, can be written as f of x plus mu transpose gx. Okay, so you have a plus here. If gx is less than or equal to 0 and mu is greater than or equal to 0. If you change this, you change the gx to be greater than or equal to 0, then you should also change this mu to be less than or equal to 0. And then you can keep this positive sign. But this will be very easily confuse yourself in the future. So I highly recommend that you just always write things like minimizing fx subject to the gx less than or equal to 0. Whatever you have, you put it on one side, and if it's greater than or equal to 0, you just take a negative sign. So just always form the inequality constraint in this way. And of course, we may have equality constraints as well. But for this particular question, it doesn't have this h at all, so we just have this g function. So once you have the g function, as I said, you just need to form the Lagrange function, and that is f, which is here, so as you can see. And then the mu1 times g1, mu2 times g2 plus mu3 times g3. But the mu1 times g1 is together is this, right? Because you have a negative sign right here. And also this is mu2 g2, and this is mu3 g3. And make sure that and you know that in this case, mu1, mu2, mu3 are all non-negative. Okay, then the KKT condition is just the gradient of this L with respect to the x. So there are two variables, x1, x2. So when we take the gradient, that means we need to take the partial derivative of L with respect to x1 and x2 individually. So taking partial derivative with respect to x1 of this one, we'll get this, and let's just set it to 0. So that's how we get the first one. Similarly, we can get this. It's the partial derivative of L with respect to x2. And then these are just the three inequality constraints of the original problem. And then we have this KKT multipliers, which must be non-negative. And then we have the slack completeness. And then we have this, right? These three. Okay, so now this all together is the KKT condition. All this together is the KKT condition. And what we're trying to do is just to solve, see if we can solve for x1, x2, mu1, mu2, mu3 from this. So you can do this computation, and as I said, you just need to do this case by case. For example, you see that if mu1 is positive, then the x1 must be 0. If mu2 is positive, the x2 must be 0. So you separate the case. Mu1 greater than 0, mu1 equal to 0, and the mu2 greater than 0. You just make all kind of combinations and see the result is. Apparently, this complexity will grow very quickly if you have more and more variables. Fortunately, we only have like 3 variables. 2 variables plus 3 multipliers. So this is still doable, right? It's still doable by hand. So at the end of the day, you will get this result, which tells you that x1 should be equal to x2 should be equal to 2.5, x1, mu1, mu2 should be equal to 0, and mu3 equals to 5. Okay, so that's the only point that satisfies this KKT. I would say this set of equations. I cannot say this satisfies the KKT yet because there's one more thing we need to check. We need to check that this point is actually a regular point. And to check that, what we need to do is first see which of the 3 inequality constraints are active, which are inactive. So when you plug this point back into the 3 inequalities, like this one, this 3, you will see that the first 2 are inactive because you plug in, they're actually strictly less than 0. They're not equal to 0. So those G1, G2 are inactive at this point. And the number 3, the G3 is active because when you plug in x1, x2, you see that this actually is equal to 0. So that means G3 is active. And the corresponding parameter, if G3 is active, then we just need to check the Jacobian of G3. We need to see that if this is a full rank matrix at this point. So the G3 is this. So the G3 is equal to negative x1 minus x2 plus 5. The gradient of G3 is just negative 1, right? That is the matrix. That is the Jacobian matrix. It's essentially a vector because we want to have G3 as a scalar value function. So that's why this is a full rank matrix. So that means the point x here is a regular point. And now you know that it's a regular point, and this whole thing together satisfies the KKT condition. So that means this point, this means that this is actually, this is a regular point, and this altogether satisfies this bunch of equality and inequality conditions. So we can claim that this point is actually a KKT point. Okay, once it's the KKT point, we need to know this KKT condition is just the first order necessary condition. So if you want to judge, if you want to tell if it is really a local minimizer, and we know that there is a second order sufficient condition that can help us to justify this. But remember that it's only a sufficient condition. Okay, so in this case, let's just see if it works, if the condition holds. So the second order necessary sufficient condition requires us to compute this set. I probably should have a tilde here. That's what I used in the notes. The idea is that this should be equal to the null space of the Jacobian of all the active constraints, excluding those with mu equals to 0. So now the only active constraint is G3, and its corresponding mu is not 0. So that means this G3 should be included for us to compute the Jacobian, and then we can take a look at the null space, and that is what this set is. Okay, so the G3, as we just computed, actually, it's just negative 1, negative 1. Then apparently this is the null space of this will be just all the vectors of the form t negative t. T could be any real number. Okay, that is the null space. So if we're going to check, and then we're going to form this Hessian or extended Hessian, that is the Hessian of f plus the weighted Hessian of the g's. But remember that the mu1, mu2, they are equal to 0. So the mu1 times Hessian of g1, that is certainly 0. Same for the mu2. and the only thing left is the mu3. So mu3 times the Hessian of G3. The G3 has this as the, actually says this. This is the gradient of G at every point, no matter what x is. So if you take the Hessian, this just gives you 0 matrix. So the Hessian of G3 is a 0 matrix. Okay, so that's why this is actually a 0 matrix. And then we only have this left. The f is this function, quadratic. So you take the Hessian, you easily see that it's just a 2002 matrix. So that is how we get that. Okay, and now you can see this is actually a positive definite matrix. So we don't even need to compute this guy here, because no matter what vector I plug in, I put on the two sides, this is going to be positive. But I showed this step just tell you, give you one example, how you're going to compute this t. Okay, as I said, I should use the t tutor. That is more consistent with the slides. Okay, so anyway, we got this matrix. So that means for any vector y that is in this space, again, I should have a t tutor. So for any vector in this set, non-zero vector in this set, we realize that is greater than 0. So that means the second order sufficient condition is satisfied. So this means that this point that we found is actually a strict local minimizer. Okay, you can do this for maximizer, and then the same strategy can be applied to every other question. I think the most practical challenge you will see is to solve this kind of system, right? That is usually the most challenging part. And apparently that you can, if you're lucky enough, you can solve such kind of things with only a few variables. But in practice, we have a problem of dimension of hundreds or even thousands or even more. So in that case, it's impossible to solve this by hand, and we have to rely on computer, and that can be tricky to do because we have a bunch of inequality constraints here, and that is generally not easy to solve. Okay, it's unlike the equality constraint optimization. Everyone in the Lagrange condition is equality. It's an equation. So in that case, that's much easier to do. So we'll not discuss, because this is the whole set of field that people have been actively working on to derive all kinds of methods, but it's more like a problem or application specific. So there is no method that can just work well for every problem. We probably have to customize the method or algorithm for a particular question. So that is what happens in practice. And as a practitioner, if you see a problem, our constraint optimization problem, you just follow the step. You know what is the property, or you know what is the KKT condition, what the property of the local minimizer should satisfy. Then you just at least form this condition and see if there's any way that I can get to the solution of this. And hopefully that you can get a solution somehow. So that's how far we can reach, at least for this class, or at least for what this theory can cover us. Okay. Okay. So that is the solution of this problem.